Enhancing processing times and detection capabilities in unmanned aerial vehicle (UAV) drone imagery for global wildfire detection is a pressing challenge, particularly with limited datasets. To address this, a segmented neural network (SegNet) selection approach is proposed, focusing on reducing feature maps to boost both time resolution and accuracy. In real-time wildfire detection, image feed and processing speed are critical. The study highlights the importance of combating feature overload through segmentation and addressing challenges arising from diverse features like objects, colors, and textures. Pixel density is crucial in retaining essential details, especially for early wildfire detection, and higher pixel density is vital for proper feature selection. The proposed SegNet approach is rigorously evaluated using a real-world dataset obtained by a drone flight and compared to state-of-the-art literature. Forests provide essential ecosystem services, including air purification, climate regulation, and biodiversity support, and forest fires have devastating effects on ecosystems, communities, and the environment. Preventing and mitigating forest fires requires concerted efforts, including controlled burns, fire breaks, and early warning systems, as well as addressing climate change and promoting sustainable land management. Advanced detection capabilities, such as those enabled by SegNet, are necessary to combat the catastrophic effects of wildfires. The methodology employs convolutional neural networks, CNNs, for image classification, emphasizing the reduction of irrelevant features vital for deep learning processes, especially in live feed data for fire detection. The study's contributions include increased processing speeds, enabling real-time detection capabilities for wildfire, increased detection accuracy of wildfire, and improved detection capabilities of early wildfire, through proposing a new direction for image classification of amorphous objects like fire, water, smoke, etc. Overall, the proposed SegNet approach has the potential to significantly advance real-time wildfire detection capabilities, enabling more effective prevention and mitigation strategies to combat the devastating effects of forest fires. Wildfire detection using unmanned aerial vehicles, UAVs, is hindered by restricted field of vision, forest canopy obstruction, and limitations in data acquisition, processing, and transmission. A four-step approach has been proposed, involving data acquisition via UAV sensors and cameras, onboard processing with learning algorithms, data transmission or reception, and notification of concerned authorities. However, balancing spatial and temporal resolutions remains a challenge, as stationary imagery offers good temporal resolution but poor spatial resolution, while mobile imagery provides good spatial resolution but poor temporal resolution. Furthermore, selecting suitable graphics processing units, GPUs, and detecting forest fires during the fall season, when tree colors resemble fire, pose significant obstacles. The density of neural networks also affects processing speeds, and limited datasets of wildfire images are available, making it difficult to develop accurate detection algorithms. To address these challenges, researchers have turned to modern machine learning approaches, including deep learning (DL) techniques, generative adversarial networks (GANs), YOLAV3, and region-based convolutional neural networks (RCNN). These approaches have shown promise in wildfire detection, but their effectiveness is limited by the lack of labeled and formatted data for training and testing. Previous studies have compared various machine learning techniques, including artificial neural networks, AN, local regression, LR, radio frequency, RF, and support vector machine, SVM, for wildfire management and forecasting. These studies have demonstrated the advantages of machine learning approaches, which are data-driven and independent of prior information. However, the use of powerful hardware, such as GPUs, is often limited by the weight and control constraints of UAVs. When an image is fed into a convolutional neural network, CNN, it contains numerous features such as objects, environment, shape, color, texture, and interactions. These features are produced by filters and collected as a feature map, with the number of pixels in an image being proportional to the information it contains. The choice of the number of features in a feature map varies depending on the engineering problem, with some applications requiring a high pool of feature maps to distinguish between different types of defects. However, a larger feature map requires a larger dataset, which can lead to underfitting or overfitting of the model. To address this, researchers often use images of 256 by 256 pixel size, resulting in a smaller feature map, but with a loss of information. This paper proposes a solution using segmentation techniques on wildfire images. By breaking down high-pixel images into smaller pieces, equal in pixel size, which can be concatenated to form the original image without losing information, the approach is suitable for detecting amorphous objects like flames. The segmentation technique enables two positive outcomes. First, flames become a prominent feature in one of the segmented images, making it easier to detect, and second, processing speeds increase as the number of pixels in the input image decreases. The paper also proposes a SegNet architecture for early wildfire detection, based on convolutional neural networks with support vector machine and ReLU classifier for convolutions. The optimal hyperplane to separate two classes can be computed using the predictor function, Manhattan norm, and penalty parameter, represented by equations 1, 2, and 3, respectively. By segmenting images into 12 segments, each 320 by 240 pixels, the algorithm can detect flames and smoke more accurately, and increases processing speeds. When integrating this algorithm within a UAV drone equipped with a 720p camera, the video feed is broken into frames, and selecting a frame every 20 frames per second helps lower computational costs and speed up processing. The proposed SegNet architecture is integrated into a drone's detection processing system, as illustrated in Figure 6, showcasing the model's ability to process images and detect fire or non-fire scenarios. A comprehensive performance analysis, presented in Table 2, reveals the impact of varying the number of convolution and dense layers on the model's processing times and test accuracy. Increasing the number of convolution layers improves accuracy, but at the cost of increased processing time, necessitating a balance between computational efficiency and accuracy. The model's performance is evaluated using different imaging approaches, with Table 3 listing the number of images in the training dataset, categorized by original, complete, augmented, and segmented images for fire and non-fire cases. To address overfitting concerns, various techniques are employed, with the accuracy improvements achieved by these techniques presented in Table IV. The initial model accuracy of 56.7% improves to 89.2% after training, but suffers from overfitting, with a validation accuracy of 59.7%. Early stopping is employed to mitigate overfitting, but yields minimal improvements. In contrast, integrating augmented images into the dataset significantly increases training accuracy to 97.5% and validation accuracy to 76.1%. The implementation of L2 regularization further refines the model, resulting in a test accuracy of 98.2%. The experimental results demonstrate the effectiveness of the proposed SegNet architecture in detecting fire and non-fire scenarios, achieving a balance between computational efficiency and accuracy. The model's performance highlights the importance of carefully selecting the number of convolution layers and employing techniques to address overfitting concerns. The use of augmented images and L2 regularization proves crucial in refining the model and achieving high accuracy. The proposed SegNet architecture offers a promising approach for real-time fire detection using drones, with potential applications in wildfire management and disaster response. The proposed SegNet model has achieved a substantial increase in training accuracy, reaching 99.6%, with a corresponding validation accuracy of 99.3%. And a remarkable test accuracy of 98.2%. This improvement is attributed to the cautious integration of techniques, including early stopping, augmented data, and L2 norm regularization, resulting in a finely tuned model that addresses overfitting and refines its generalization capabilities. A comparison with state-of-the-art literature algorithms, including GoogleNet and AlexNet, demonstrates the effectiveness of the proposed segmentation approach. The results show that SegNet outperforms both GoogleNet and AlexNet in terms of accuracy, with train accuracy of 99.6%, validation accuracy of 99.3%, and test accuracy of 98.2%. In contrast, AlexNet achieved a train accuracy of 100%, test accuracy of 92.2%, and validation accuracy of 91.3%. While GoogleNet achieved a train accuracy of 99.9%, test accuracy of 76.8%, and validation accuracy of 77.5%. The proposed SegNet approach is designed to reduce processing times and minimize computational power requirements. The processing speed of the SegNet approach is observed to be faster than both GoogleNet and AlexNet, with an average processing time of 240.37 milliseconds per complete image. This is achieved through the use of a segmented approach, where a single batch of 32 segmented images takes an average of 641 milliseconds to process. The memory requirements and time complexities of the SegNet architecture are detailed in Appendix A. The proposed SegNet model consumes 44.17 megabytes of memory and performs a total of 19.275 million operations. This makes it suitable for deployment on a drone with a processor speed of at least 19.275 MHz. The performance metrics of the SegNet model are presented in Fig. 9, which shows the accuracy, precision, and recall rates of the model. The results demonstrate that SegNet performs on par with most modern machine learning approaches, with a high recall, precision, and accuracy rate of 98.18%. The model's effectiveness is further testified by the number of true positives, true negatives, false positives, and false negatives observed in the test data. Overall, the proposed SegNet approach demonstrates its effectiveness and reliability in the realm of wildfire detection, making it a potent tool for this application. The proposed segmented neural network, or SegNet, is compared to state-of-the-art models, including AlexNet and GoogleNet, in terms of training and validation accuracy and losses. As shown in Figure 7, SegNet demonstrates superior performance, achieving high accuracy while minimizing processing time. Furthermore, the temporal categorization latency chart in Figure 8 highlights SegNet's efficiency in real-time applications, showcasing the time required to perform classification tasks with different batch sizes of input images. This research introduces a novel approach to wildfire detection, leveraging the power of convolutional neural networks to enhance time resolution and optimize processing speeds while maintaining high accuracy levels. By breaking down high-resolution images into smaller, manageable segments, SegNet allows for rapid processing without compromising accuracy. The study addresses the complexities of feature reduction, implementing techniques such as early stopping, data augmentation, and L2 norm regularization to mitigate overfitting, enhance generalization, and achieve outstanding accuracy rates. The results demonstrate a significant leap in accuracy, with the final model achieving an impressive 98.2% accuracy on the test dataset. The segmentation approach outperforms established models, showcasing not only superior accuracy but also remarkable processing speeds. The algorithm processes a complete image of 1280 x 720 pixels in just 240.37 milliseconds, making it suitable for real-time applications. Beyond accuracy and speed, this research emphasizes the importance of preserving essential details in images, especially in early wildfire detection scenarios. By ensuring the amorphous nature of fire, features are retained through segmentation, allowing the algorithm to excel in detecting subtle signs of wildfire, crucial for timely intervention. Additionally, the algorithm's integration within unmanned aerial vehicle drone systems is highlighted, optimizing resource utilization and minimizing computational costs. This streamlined approach significantly reduces production costs and drone weight, ensuring practicality and efficiency in real-world deployments. The authors present the performance metrics of the proposed SegNet model, including true positives, false negatives, and true negatives, as well as derived metrics such as false positive rate, false negative rate, true negative rate, recall, accuracy, and precision. These metrics are calculated and presented in Figure 9 and Table V, with a detailed mathematical formulation provided for each metric. The time complexity of the SegNet algorithm is analyzed using big O asymptotic notation, allowing for a comparison with existing models such as AlexNet and GoogleNet. Key variables considered in this analysis include the number of weight elements, kernel size and channels, number of kernels, neurons in the output dense layer, and memory size for float64 datatype elements. The time complexity of the SegNet model is further analyzed with respect to changes in image size, with the total number of operations per convolution layer given by equation 5. Simplifying this equation reveals a linear time complexity in 2 dimensions, m and n, with a big O notation of O, m, n. This analysis highlights the model's efficiency in handling varying image sizes. The authors also discuss the memory requirements and operational complexity of the model, with mathematical expressions provided for model space complexity, operational space complexity, and operational compute complexity in equations 710. These equations enable the calculation of the total operational space complexity per layer, providing valuable insights into the model's computational requirements. A detailed calculation of performance and time complexities is provided in the appendix, offering a comprehensive understanding of the SegNet model's capabilities and limitations. Please provide the content from the research paper that needs to be refined, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided.